Hi guys. So today we are going to be looking at the determination of empirical and the molecular formulas. So before we start, let's try to understand what is the meaning of empirical formula, what is the meaning of molecular formula, and then there's also another formula called structural formula. So what is an empirical formula? Empirical formula is the simplest whole number ratio of atoms in a compound. For example, water and H2O2. As you can see, water is 2:1 ratio of hydrogen and oxygen. H2O2, the whole number ratio is 1:1, although H2O2 is 2:2, but you simplify it, that's how you get 1:1. So the empirical formula is HO for H2O2. That is the hydrogen peroxide. Next is the molecular formula. Molecular formula is what you normally see, when you look into the chemistry, balancing equations and so forth. So there you see the number of each type of atoms that are present in a molecule. For example, H2O. Now, H2O contains 2 atoms of hydrogen and 1 atom of oxygen. H2O2 contains 2 atoms of hydrogen and 1 atom of oxygen. So here you're not going to simplify it. You're not going to say it's 1 atom of hydrogen and 1 atom of oxygen. No, it is the exact number of atoms that make that molecule that are shown in the molecular formula. Molecular formula is a more stable form of that particular combination of atoms. Empirical formula is just a very basic, like just a simple ratio, just a numerical value. Okay, then there is a relationship between the molecular formula and the empirical formula, and that relationship is of the formula units. How do we calculate that? You take the molecular formula mass, divide that by the empirical formula mass, and the number n, the value of n, that is your formula units. And we are going to look further into how we are going to use the value of n in determining the molecular formula if we know the empirical formula and the mass of the empirical formula. So anyways, just let's look at the structural formula. Structural formula actually tells us what is the connectivity of the atoms, at what angle the certain atoms connect or are bonded. So those angles, for example, in water, if hydrogen and oxygen are to combine, that bond is only going to happen if the angle is 104.5. Nothing more, nothing less. So oxygen will be in the center and not hydrogen. Oxygen has a capability to make 2 bonds. So that is why oxygen will be in the middle, hydrogen on the side, and this is the structural formula. So structural formula gets more in depth into the bonding. Look at H2O2. H2O2, again, oxygen on one side is combined with hydrogen, and oxygen on the other side is bonded with oxygen. And this central oxygen, on that, the one that is on the side, that one is at 94.5. So there is a certain bond angles, bond length, and those distances, all those come to play when we do the structural formulas. So structural formulas, we are going to see the structural formulas when we study the Lewis structures. That tells us, how these are bonded. But for now, let's focus our work here on the empirical and the molecular formulas. But even before we go into that, how do we come to the empirical formulas? How are the empirical formulas determined? So there is a technique called the elemental analysis. For example, you have an organic compound that contains carbon, hydrogen, oxygen, maybe chlorine, maybe nitrogen, maybe sulfur, and so forth. Okay, so this sample is burnt in a furnace. So it is first a decomposition reaction and it's a combustion later. So what happens is that a blast of oxygen is blown into a furnace in which your sample is being burnt. Oxygen combines with carbon, oxygen combines with hydrogen to form carbon dioxide and water respectively. Then these two gases, along with the other gases that are liberated in the combustion, these gases move down the stream, and they move to the next chamber. One of the chamber contains magnesium sulfate, which absorbs water. So you take the weight of magnesium sulfate before, then you take the weight of magnesium sulfate after. The difference in the weights is going to give you how much water has been absorbed. Where has the water come from? The water has come from the sample when hydrogen itself combined with oxygen. So basically, we are looking at hydrogen in this section. Next, the gases move to the next chamber, which is containing sodium hydroxide. So you take the weight before, then you take the weight after the combustion. So the before the combustion and the after the combustion, the difference is going to give you how much of carbon dioxide has been absorbed by sodium hydroxide. Now, where did carbon dioxide come from? Carbon dioxide has again come from when carbon from the sample, a certain amount of carbon from the sample combined with oxygen. So then it produced carbon dioxide, which got absorbed by sodium hydroxide. And then the rest of the gases are accounted for, are sometimes they are, tested, sometimes they are like just computed. Okay, so this is this elemental analysis. It is a combustion analysis process in which we get a very simple whole number ratio of each element. Then what about the molar masses? How do you get the molar masses? Now in the industry, there is a machine that we used, which is called the LC mass spec. And that LC mass spec is a liquid chromatography mass spectrometry. It's an apparatus, it's a machine that gives you how much is the molecular weight of the sample. There are so many other ways you can calculate the molecular weight also, or you can get the molecular weight through some experiments. However, we are going to focus more on how do we calculate the empirical and the molecular formula of a sample when the percentages are given to you, or if you know what percent is carbon, what percentage hydrogen, and a certain percentage of chlorine, and so forth. So let's look at this sample. So we have a sample that contains carbon, hydrogen, and chlorine. Okay, so in this sample, we found that we are given 24.3 grams of carbon. We are given 4.1 grams of, 24.3% carbon, 4.1% hydrogen. And we also know that there is chlorine also present in this sample. We are also given that 99 grams per mole is the molar mass of the sample. That is already known. So we need to find the empirical formula and we need to find the molecular formula. Okay, now first thing first, what is the meaning of this percentage? Percentage means that the whole sample is 100 grams. And in that percentage, you're going to take carbon, convert the carbon, the given carbon, convert the carbon to grams. In other words, that 24%, 24.3% carbon means 24.3 grams of carbon. Similarly, 44.1% hydrogen means 4.1 grams of hydrogen. And then you add the 2 grams together and you subtract them from the total 100, and you're going to get 71.60% chlorine, and that equals 71.60 grams. Okay, so now there is a certain steps when you do the computation to get the combustion analysis, to get the empirical formula and the molecular formula. There are certain steps. So what are those steps? Just look at these steps. So the first step always is, like I showed you, take the percentage, convert that to grams, convert the grams to moles using the molar mass. Okay, so this is through the molar mass. That gives you the moles of each atom that was in the sample. Next, you're going to take the mole to mole ratio. That is, you're going to divide those moles by the lowest value of the moles. Now, sometimes you have to get the whole number in order to get that. Now, how do you get the whole number? Either you simply round up, or it's okay to round down here. So either round up or round down. Next thing, if that doesn't work, you have to sometimes multiply by some number in order to get the whole number. Okay, to get the whole number, you multiply that by some number. So that's going to give you the mole to mole ratio as whole numbers. You need those whole numbers for the mole to mole ratios. Okay, then you plug them in the empirical formula. In other words, you plug them in with the particular atoms, and then you're going to get the empirical formula. Next is you're going to do the empirical formula mass. In other words, just like you calculate the molar mass, you're going to calculate the empirical formula mass also. Okay. Then you're going to take the molecular formula mass that is given to you, and you are going to divide that by the empirical formula mass, and that gives you the value of N. Now, what is N? N is the formula units. You need these formula units per molecule. Okay, you need these formula units. These formula units, they're then multiplied by the empirical formula mass, and that's going to give you the molecular formula mass. So this is the roadmap we are going to follow. Now let's look at this problem. So now we have, I'm going to just write down the first step we already did. We took the percentage, you converted that to grams. Simple. Next, we are going to take carbon, hydrogen, and chlorine, do our first step, which is carbon, hydrogen, and chlorine. Carbon, convert that to moles. So we are given carbon to be 24.3 grams. Okay, hydrogen is 4.1 grams, and chlorine is 71.6 grams. Convert that to moles, all three of them. So we are going to take we know that 1 mole of carbon. Now I'm going to use the exact numbers as I see from the periodic table, and it's okay to do that. So don't round it up right away. 011. So this is the number I see, 12.011 grams of carbon on the periodic table. 4.1 grams, 1 mole of hydrogen is 1.0079 or 8 grams of hydrogen. So this is again the exact mass number of hydrogen element as I see on the periodic table. And then comes chlorine. Chlorine is 71.6 grams of chlorine, and that is equal, sorry, 1 second, I'm sorry. So this is 1 mole of chlorine. 1 mole of chlorine, 1 mole of chlorine is 35.453 grams of chlorine. Okay, so when you do the math, 24.3 divided by 12.011, 4.1 divided by 1.0079, 71.6 divided by 35.453, and that's going to give you 2.02 moles of carbon, 4.07 moles of hydrogen, and 2.02 moles of chlorine. Okay, so this is your first step. Now you have the moles. Next step is the mole to mole ratio. So let me just write this down here again, that this is the grams to mole conversion. Next step is the mole to mole ratio. Mole ratio. So how do we do this? We are going to take, now the lowest moles are, it doesn't matter whether it's carbon or chlorine, still the lowest moles we got is 2.02. Okay, so now you're going to take carbon, hydrogen, and chlorine, and here you are going to put 2.02, let's do this, 2.02, that's the moles of carbon, divide by the lowest moles, 2.02. Hydrogen is 4.07, divide by 2.02. Okay, and we have chlorine, and chlorine is 2.02 divided by 2.02. So that gives us carbon is 1, hydrogen is 2, and chlorine is 1. Okay, so next is the empirical formula. So plug these numbers in the empirical formula. Okay, and that is going to be the third step, and that is carbon 1, hydrogen 2, and chlorine is 1. So in general, it is CH2Cl. So this is a very simple whole number ratio, although it doesn't make sense because carbon should be making 4 bonds, but if it has only 3 atoms bonded to it, so that it's not stable. So this molecule is not stable. So it doesn't make sense. So we need to, in order for it to be stable, we need to look at the exact molecular formula so that it makes sense. Like, okay, so it needs to make the appropriate number of bonds in order to be stable. All right, so now we are going to look at the next step, which is calculating the formula unit. And that formula unit is the value of N. Okay. All right. So here we have the, this was 1. So we have to first calculate the empirical formula mass. Okay. So CH2Cl. Okay. So CH2Cl. So this means that 1 carbon atom times 12 grams of carbon. Now this is from the periodic table, and we have 12 grams of carbon. We have 2 hydrogens, each is 1 gram, and we're going to get 2 grams of, so that's carbon, that's hydrogen. 1 atom of chlorine times 35 grams, and you are going to get 35 grams of chlorine. So when you add all of this together, this gives you the number 49.5. 49.5 grams per mole. And this is the value from the empirical formula mass. Okay, empirical formula mass. And that is 49.5. Now, we know that which is given to you. So we are given the molar mass, and that molar mass is given is equal to 99 grams per mole. Okay, grams per mole. So we have now the formula, which is the molecular formula mass. Okay, molecular formula mass divided by the empirical formula mass. Okay, and that is going to give you the value of N, the formula unit per mole. Actually, this is formula unit per mole, molecule, sorry, per molecule. This is for 1 molecule, in other words. That's what it means. Okay, so now we are going to take our, just plug in the numbers. So that is molecular formula mass 99, empirical formula mass 49.5. All right, so that is going to give you the numbers. This equals 2. Okay, so when this is 2, this means that now the value of, this is the value of N. So the other formula is the empirical formula mass, times the value of N, and that gives you the molecular formula. So this is your other formula. Now you are going to take the 49.5, that is the empirical formula mass, times 2, and that is going to give you the that means that in reality this means that CH2Cl whole twice, or in other words times 2, if that works for you, times 2. Okay, times 2, and that is C2H, 2 times 2, 4, Cl2. Now this makes more sense because it is there's a connectivity First of all, this thing should equal to 99 grams per mole. So you can check that way. But another way, you can also check, draw a Lewis structure and see if it makes sense. And it does. So you have C, and it's going to be several other structural formulas are also possible. So CH4, H, say H4, and Cl2. So this is one. So carbon is making 4 bonds, hydrogen makes 1 bond, chlorine makes 1 bond. So this is a stable structure. Or you can also do C, hydrogen, 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 and this is chlorine, chlorine, hydrogen. Okay, so CH4, Cl2, and C2. So this makes more sense. And then, so this is these are the different, these are the 2 different structures that are possible. And these are 2 different compounds. However, this in organic compounds, there are different types of possibilities. However, here, what's important is that this value, this structure is the molecular formula. So this is how you're going to get when you do these problems in which the empirical formula and the molecular formula is needed to be found when you are given a sample, from the percentage problems, okay, from the percentage of the samples. Okay, so anyway, so this is your one set, and I hope you found it helpful. All right, and thank you for watching. Bye.